Hi everyone, we are team Light.kxkj. My name is Kersing and I'm working with my teammate Kaijie. Today, our topic will be about disrupting deepfake. To start off with the introduction, so what is deepfake? To put it in a simple layman term, with the original input of a person's face, the system adds such small perturbation or modify a certain kind of targeted attribute such as hair color or age, then the system will generate a new manipulated image or video. It then coins as deepfake. So the overview of our project is that we want to prove that with the imperceptible perturbation we add, it is able to disrupt output image and fool any kind of deepfake detector. So instead of focusing purely on deepfake only, we actually also included some adversarial attacks as the deepfake disruptor. So these are the attacks that we have been using throughout the semester and they will be further discussed in the later slides. With the perturbed output from our deepfake disruptor just now, we now pass them as an input to StarGun, and StarGun will act as a facial manipulation system. So how the StarGun work is that it is conditioned based on a target attribute. We will basically attack based on attributes such as black hair, blonde hair, brown hair, male, and also young. The following slides will be related to the modifications we have made. So first of all, the original GitHub clone consists of different Python files that should work together. It will be troublesome for us to use the code within Google Colab. So we actually only take the necessary code and combine them in our Google Colab. So instead of using TensorFlow 1, we actually converted and updated to use TensorFlow 2 to make sure that it works fine. We also created an additional helper function to save the adversarial output to the respective folder. So we also use extra if-else statement to save the final distorted output to the respective folder. Under StarGun data loader, we actually updated the test directory to only contain the adversarial output that we generated. Talking about adversarial attack, except for FGVM attack, different epsilon value are set ranging from 0.01 to 1. We realize that the higher the epsilon value, the level of distortion of the image is more obvious to a human naked eye. So let's see. The first attack is FGSM attack, fast gradient sign method. The main idea is that based on same back-propagated gradient, FGSM adjusts input data to maximize the loss. So as you can see, this adversarial output here, we can see that it's actually heavily distorted. The next attack is IFGSM. The main idea is that by applying the same step as FGSM multiple times iteratively with a small step size, we are able to get this adversarial output here. Next up will be MIFGSM, Momentum Iterative FGSM attack. The idea is that we integrate momentum into iterative FGSM attack, and it accelerates gradient descent algorithm by accumulating a velocity vector in the gradient direction of the loss function across iterations. And if you compare the input and the adversarial output here, we can also see that the adversarial output is actually also successfully perturbed. The last attack will be FGVM attack. This is a similar attack as compared to FGSM, but the main difference is that there's no epsilon constraint on each pixel. Next up, I'll pass the time to Kaijie to continue with the presentation. That's all from me. Thank you.
Thank you, Kersing. I'm Kaijie, and I'll start with StarGun. So what is StarGun? StarGun is a method performing image-to-image translation among multiple domains using a single model. It can translate images from any source domain to any targeted domain. What is domain, you may ask? For instance, people who have black hair is considered as one domain, and people who have blonde hair is another domain. StarGun can transfer facial attributes and synthesis facial expression. When compared to the existing method, StarGun generally generate better visual quality images. In our attempt of disrupting deepfake, we use StarGun as our facial manipulation system. Next, I'll talk about the output of our StarGun model. All right, before I talk about the output, let me briefly explain what we use our StarGun model for. So we use our StarGun model to translate our input images to the 5 domains selected, which are the black hair, blonde hair, brown hair, male, and young. So over here, the first output is the output of our StarGun. So this images is the output of our StarGun. with the perturb output of FGSM with epsilon 0.01 as the input. Overall, you don't really see that much of disruption now, but then you'll see more in the next few slides. And next is also FGSM, but this time with epsilon 0.5. Also FGSM, but with epsilon 1. As you guys can see, as the epsilon increases, the disruption of the deepfake will also increase. In this case, we can conclude that if you want to have more disruption in the deepfake, we have to increase our epsilon. After FGSM, we have IFGSM. This one is with epsilon 0.01, 0.5, 1. Next is IMFGSM with epsilon 0.01, 0.5, 1. Lastly, FGVM. Since FGVM doesn't depend on epsilon, so we can't use epsilon to increase the disruption. With all these examples, I can confidently say that our attempt in disrupting deepfake is a success. And yeah, that's all about our team. Next, I'll talk about our targeted team. So our team targeted Light.Blackpink fans. What did Light.Blackpink fans achieve? So they tried to classify real and fake images using frequency spectrum analysis method. They successfully built 2 deepfake detectors, which are the 2D power spectrum and 1D power spectrum. According to them, fake images usually exhibit a criteria at a higher frequency, which means real images will exhibit a criteria at a lower frequency. The goal of our team is to try to bypass the 2 deepfake detectors that they built, and I'm going to explain the outcome of our attempts in the next few slides. So the first detector is the 2D power spectrum. So the real image is from the Celeb A dataset. After passing it into the 2D power spectrum, we'll get the image on the right. And the fake image is the output of our Stargardt model with the perturbed output of FGVM as input. And passing it into the 2D power spectrum, we'll get the image on the right. So the images on the left are the images that we obtained from Light.Blackpink fans. All right, so over here, when we try to compare the 2D power spectrum of our images to the 2D power spectrums that we obtained from their images, we can say that the 2D power spectrum of our fake image is more similar to the 2D power spectrum of their real image than their fake image. The 2D power spectrum of their fake image display a grid-like structure at a high frequency, but not in the 2D power spectrum of our fake image. So in this case, our fake image will be classified as real. And next is the 1D power spectrum. So the real image is also from Celeb A dataset, and passing it into the 1D power spectrum, we'll get the line charts. And the fake image is the output of our Stargardt model with the perturbed output of FGVM as input as well. And passing it into the 1D power spectrum, we'll get the line chart. As you guys will notice, the spatial frequency of our fake image is twice the spatial frequency of our real image. And you guys might think that, oh, in this case, the 1D power spectrum will classify our fake image as fake. However, when we compare the spatial frequency with the spatial frequency that we obtain from the with the spatial frequency of images that we obtain from the Light.Blackpink fans, you will think otherwise. So the images on the left are the images that we obtain from Light.Blackpink fans, and we can see that the spatial frequency of their fake image is more than 700, whereas the spatial frequency of their real image is around 350, and the spatial frequency of our fake image is less than 300, which means it's less than the spatial frequency of their real image. So in this case, 1D power spectrum will classify our fake image as real. And yeah, that's all from me and Kersing. Thank you for listening. This will mark the end of our FIT3183 project assignment. Thank you.